In this problem they have said a rotating shaft consists of 4 masses, that is M1 is equal to 18 kg, M2 is equal to 14 kg, and M3 is equal to 16 kg, and M4 is equal to 12 kg, which is having a radial distance of 5 centimeter, and the R2 is equal to, that is which is having a radial distance of R1 is equal to 5 centimeter, R2 is equal to 16 centimeter, and R3 is equal to 7 centimeter, and R4 is equal to 6 centimeter. That is the radial distance from the geometric center to the center of mass of that particular masses, that is M1, M2, M3 and M4. And then there I have said another thing, that these planes, that is these masses are located at a distance of 8 centimeter from your plane M1, that is M2 is located as 8 centimeter from M1, and 16 centimeter, that is M3 is located at 16 centimeter from M1, and M4 is located as 28 centimeter at M1. So this is the position of planes I have drawn. I have not mentioned over here. For our better understanding, I have placed over here such that I have said that these masses, that is M2, M3 and M4 are located at that 80, that is I changed in terms of mm, that is 80 mm from M1, and 160 mm, that is M3 is located as 160 mm from M1, and M4 is located as 280 mm from M1. Okay. Then that I also said that M2 is located at M2 and M3 and M4 are located at, that M2 is located at 60 degree from M1, and M3 is located at 135 degree from M1, and M4 is located at 270 degree from M1. There I said everything is located at from clockwise direction. These all the masses have been located at with respect to M1. Okay. So, and then there I have said, in order to bring this total system into dynamically balanced condition, they are saying they have brought two masses, that is two masses I have taken over here as X and Y, which is at a radial distance of 5 centimeter. That is both the masses, that is balancing masses, that is Mx and My, both are going to be at 5 centimeter from the center of the shaft. That's what I would have given to be as Rx is equal to 5 centimeter and Ry is equal to 5 centimeter. And then there I have said, and these balancing masses Mx and My, and then that I have said these balancing masses Mx and My are located at midway between the first and second plane, that is X is, that is balancing mass X is located midway. So what is the from midway? We know that the distance between 1 and 2 plane is 80. So Mx is located at 40 mm between 40 mm from M1. And then there I have said the second balancing mass located midway between third and 3 and M4 with respect to the first plane. We know that M3 is located as 160 mm and M4 is located as 280 mm. So 280 minus 160 will tends to get 12 mm, that is 12 mm. So midway between, so midway is 60. So from M1 it is located at 220 mm. So with respect to mass M1, we have kept all with M1, we have kept X and Y, M2, M3 and M4. So we are taking, we have put the balancing masses Mx and My at the specified location as per is given in the problem. And then this figure is called, this is also a space diagram figure. This figure is called as position of planes. With respect to the question has been given, we have constructed this plane, and then we have to, another space diagram will be your position, that is your angular position of planes or angular position of masses. So angular position of masses plays a very important role, as we have seen the problem in balancing of masses in single plane. So we are taking M1 as reference. So for instance, we are taking always theta 1 is equal to 0 degree. So I am going to take, with respect to an O point, I am going to take M1 is going to be at 0 degree, that is our M1, and then they have said from M1 our M2 is located at 60 degree clockwise direction. So 60 degree clockwise. So our M2 is located at 60 degree clockwise. So this is with respect to M1. And then that I have said our M3 is located at 135 degree from M1. So 135 degree from M1. So this is our M3, which is located at 135 degree from M1. This we have to draw with respect to the protractor, as well as for position of planes also. You need not to specify with the dimensions and all. It is for general understanding. We are not going to do anything with respect to the position of planes figure for further drawing. Whereas angular position of masses alone we will be utilizing for drawing the force polygon as well as couple polygon. So it should be very much clear such that. So we have to be very concentrating on placing the angular distance between with respect to M1, and then there I have said 270 degree our mass M1 is located. So our M1 is located at 270. So 270 degree from M1. That is our. Moving on to the problem. Whenever the problem is asked in balancing of several masses in different planes, first approach we need to draw the position of planes, and then we have to draw the angular position of planes. After drawing those two figures, we have to straight away go to the tabular column. So with this tabular column only, it is very useful for us to construct the force polygon as well as the couple polygon also. So how we are going to construct this for reference tabular column is very much important. First of all, we have to segregate this in such a way. First we have to take in the concept of plane, and then the mass in terms of kg, and the radius m, that is radius in terms of meter. What is that radius? That is the radial distance of the each masses from the geometric center. So that they are given to in the problem for M1 that are given to be as 5 cm. I have written in terms of meter. As respect to that, and then we are finding out the centrifugal force. We know that centrifugal force here is m omega square. In terms of the equation is getting cancelled. We know that centrifugal force is mass into radius. That's what I have written, m into r, that is kg meter. And then distance from reference plane. This is very much important. This is very much important in terms of your solving the problem. We have to consider any of the one plane to be as the reference plane. I will say why we are considering a reference plane and how we have to choose a reference plane. I will be saying you, and distance from reference plane, and then couple. Couple is nothing but this centrifugal force into the distance, m into r into l. That's what. When you are going to multiply the second and third tabular column, you will be getting the centrifugal force, and when you are going to multiply the third, that is your fourth and your fifth tabular column, you will tend to get your couple tabular column. And then that's what. Then I have written the mass possessed by each mass. That is plane 1. That is mass 1. That at plane 1 we are having what? That is mass 1. That is possess 18 kg. And then at plane 2, after very next to our mass plane 1, we are having plane x. That is mass x. That I am given to be as mx, and then accordingly I have given for m2 and m3 and then my. That is your mass. That is at y plane we are having my, and that fourth plane is our last plane. That is having a mass of 12 kg, and then the radius accordingly, the radial distance they are given in the problem for each masses, and then they are said in the problem the balancing masses, that is mx we have taken, I consider it to be as x and y. They are given the radial distance of the balancing masses to be as x and y. They are given to be as 5 cm. I consider to be as 0.05, 0.05. And then till here you can able to see. So limit of here till here you are getting the centrifugal force value. As we have seen in balancing of several masses in single plane, we will be multiplying only the mass into radius, we will be getting the centrifugal force. So here next we are moving on to the couple tabular column. To arrive at the couple tabular column, we are very much interested to determine the L distance. As we discussed in the topic, we are very much interested in the L distance. That is the distance between the each masses located at different planes. So for that instance, we have to take any of the one plane to be as the reference plane, such that so it will simplify our problem in a very big manner. So that I will say why we are taking one of the plane or why we are selecting a particular mass to be as the reference plane, because when you are going to see here, that is number of unknowns in the centrifugal force tabular column, we are having the number of unknowns to be as 2. There are two unknowns, mx and my. So in order to make and then we also know that the couple polygon will tends to get the multiplication of your centrifugal tabular column into distance from a reference plane. We will be able to arrive at the couple polygon. In order to make any of the one quantity to be as 0, we have to consider any of the reference plane which is having an unknown mass, to be as the reference plane mass. So for that instance, I am going to take x as to be my reference plane. That's why we are taking x to be as the reference plane. So for that instance, when you are going to move on to the thing, so when I am going to take x as the reference plane, so when I am going to take x as the reference plane, we can able to see from x to the left negative directions we are having m1. That's why I have given minus 0.04. This is applicable to all the problems. Whatever the masses are, whatever the mass that has been located in the left hand direction with respect to the reference plane calculation, we have to give the negative notation. So I have given distance from reference plane, that is x, or m1 is located as minus 0.04 in terms of meter, and then distance from reference plane itself, it will be 0. So it is 0, and then m3 is located at, that is distance from of m3 from, distance of m2 from mx will be, again it will be 0.04, and it will be going on for m3 is located at, mx is located at 0.12 meter, and then our reference, one of the balancing mass mo is located as 0.18 meter from mx, that is reference plane, and then m4 also is located as 0.24 from mx plane. That is because we can able to, for simple calculation I am saying, m4 is located at from m1 it's located as 280 m1, and then mx is, the distance between m1 and mx is 40. So when we can able to calculate the distance between the mx plane as well as m4 plane, that is m4 plane, that is going to be 280 minus 40 will tends to get 240 mm, that is 0.24 meters. So multiplying the value of the centrifugal force as well as the distance, we will tends to get the value of the couple values. So we are getting the couple values over here. So, and then with respect to the centrifugal force tabular column, we can able to construct the force polygon with respect to the space diagram of angular position of different masses, and then we can able to construct the couple polygon with respect to the values we obtained from the couple polygon value, and then we can able to determine the values of mx and my, that is the balancing masses mx and my, and then the orientation of theta x and theta y with respect to the couple polygon and then the polygon. So when you are looking at the tabular column, you can able to see we have to select whether we have to draw the couple or force polygon. It depends upon the number of unknowns in each tabular column. In the centrifugal force in the tabular column, you can able to see mx and my, there are two unknowns are over there, whereas in terms of couple polygon, you can able to see there are only one unknown is over there. So in such that we can able to move on to the directly in terms of couple polygon directly. So after with the help of the couple polygon, we can able to determine the value of my with respect to some vector value, and then we can able to we can determine the value of my. Substituting the value of my will reduce the centrifugal force tabular column with one unknown. So we are moving on to the hence we are moving on to the couple polygon. So you can able to see in the couple polygon. So before drawing the couple polygon, you have to specify the scale. Here I am going to take the scale. 1 centimeter is equal to 0.025 kg meter square. Okay. So first of all, initially I am going to draw the couple polygon value with respect to. So I am going to place the center value as to be as O. So with respect to the angular portion of masses only, we can able to construct the couple polygon as well as the force polygon. So from here, with respect to the O point, we can able to see if it is given to be the value of minus 0.036. So minus 0.036 is the vector value of the mass 1 couple polygon value. So since it is in the negative direction, we are going to draw in the opposite negative direction. When you are going to divide the value of that is my 0.036 divided by 0.025, you will tend to get the value in terms of centimeter. So I am going to draw the couple polygon value of, so with respect to parallel with respect to the M1, I am going to draw the OA vector. So that OA vector is nothing but, that is our OA. Okay, so since why we are drawing not drawing on this direction, we are drawing in this direction because it has been in negative direction, it is radially inward. So we are going to draw in the opposite direction to that, and then x we don't know, so we need not to consider about x, and then we are going to the mass, that is your mass 2. So our mass 2 is located at this direction, so we are going to draw our mass m2. So that also it has been given to be as 0.036. With respect, when you are dividing the value with respect to 0.025, you will tend to get in terms of centimeter. So this would be your, so I am going to draw it parallelly. So I am going to get it to be as having the value of 0.1344. When you are going to look over there, you can able to see the value of your, so when you are going to divide that value with respect to 0.025, it tends to get in terms of centimeter. So this is your mass 3. I am going to draw parallelly exactly with respect to that. So I am going to get the value of to my C. This is my C. So since then we will have to move on toward mass 4. Since we don't know the vector value of 0.09 my, the such therefore parallel with respect to here. So we will tend to get our mass m4. This is our value of D. Okay. So this is in the upward direction. And then the closing vector, that is when you are going to connect your vector OD, this value will tend to give you the, so which is will be in the opposite direction. So it will be the opposite direction. This will tends to give us the mass, that is the vector value of our mass Y possessed, that is 0.009 my. 9 my is equal to vector OD. So our vector OD value is 0.12. So when you are going to multiply with the appropriate scale value, you are going to get the value. So from here we are getting the value of my should be equal to 13.3 kg. So after determining the balancing mass M, we are in a position to determine the value of our theta y, that is the mass placed in the angular position plane with respect to the M1. We know that the earlier being from OD vector, we can able to get, we are going to draw parallel with respect to the OD vector. We are getting the resultant vector, that is our FR of Y. So exactly parallel to this, so FR Y. So exactly parallel to this, we will be having the value of My. When you are going to measure from M1 in clockwise direction, our My will be placed at 25 degree. So the theta y is equal to 25 degree. So from here we have determined the value of our my and theta y from the coupled polygon, and then since we determined the value of my, when you are going to utilize this value of my in the force, in the centrifugal force tabular column, we will be reduced to one unknown, that is mx. So similar with respect to the similar steps, you can able to determine the value of mx as well as force polygon. So before drawing the force polygon, we have to know that 0.05 my. So we have got the value of my is equal to 13.3 kg. We are going to multiply the value of my over here. So from that we will get reduced the number of unknowns from 2 to 1 in terms of centrifugal force vector, that is centrifugal force tabular column. So from here you can able to know that with respect to the same procedure earlierly we did. So OA, so before that we have to take a scale 1 centimeter is equal to, I am going to take a scale of 1 centimeter is equal to 0.5 kg meter. So we are going to divide the value of 0.5 with respect to the value we have to get. So I am going to draw parallelly exactly over here. I am going to get a value of O dash. So I am going to give in terms of dash. So parallelly, and then moving on to, so since we don't know the value of x, so we are going to the mass 2. So mass 2 exactly over here. So when you are going to draw parallelly over here, respect to here, we will get B dash. So that is from the vector value of 0.84 divided by 0.5, will tends to get the value in terms of centimeter. So that we are drawing over here, and then we have to move with our mass 3. So mass 3 is 1.12 kg meter. So this 1.12 kg meter we are going to draw parallel over here. We will be tends to get, so our value is 1.12 divided by 0.5, will tends to get the value in terms of centimeter. So you have to draw parallel with respect to, so we are getting a value of C dash. We have to go with the mass 4. First we have to finish off all the unbalanced mass, and then only we have to move on to the balanced mass condition. So then our mass M4, that is 0.72, we have to place it parallelly. So parallel we are going to draw, we will be getting the value of your D dash. So for our better understanding, we will tend to get this to be as FC1 and FC2 and then FC3, and then this is going to be our FC4. and then at last we are going to draw our my, that is the unbalanced mass, which we have known the value to be as 0.665. So we know that our mass is placed in this direction. When you are going to draw this to be as parallelly, we will tend to get, so parallel with respect to that. So this is going to be a D dash to E dash. This is going to be a FC of Y, that is balanced mass. And then the closing vector will tends to give us the O dash to E dash will tends to give us the value of our FC of X. So from here we can able to get that 0.05 mx is equal to vector O dash E dash, which from the measurement we can able to get 0.54. So from here we are getting the value of mx is equal to 10.86 kg. So since the resultant force vector is placed in the downward direction, so we have to draw it parallelly the resultant force vector. So that is our FC X of R. So exactly opposite to the, along the line of action, we will be having the mass mx, which will be located when you are going to measure from the m1 in clockwise direction. It will be located at 285 degree. So from that we have determined my is equal to 13.3 kg, theta y is equal to 25 degree from m1 clockwise, and our mx is equal to 10.86 and theta x is equal to 285 degree from m1 clockwise.